So key points for today on acceleration. Acceleration is not a new concept. You talked about it in Science 10, okay? The definition of acceleration is very simply any change in velocity over time. Okay, that's what we call acceleration. Okay, we need to learn the relationship between change in velocity, distance, time, and acceleration. So one formula you're familiar with and 4 that you aren't. Okay, by the time this is all done, we'll have 5 formulas involving accelerated motion, okay, for you to choose from for problem solving, and then obviously be able to solve problems using those formulas. And that's what we'll be looking at today. So essentially, we'll just review what acceleration is, and then I will walk through all 5 formulas. We'll do some examples of problem solving using each of those formulas, look at manipulation, etc. Okay, and then probably tomorrow we'll spend kind of practicing using those formulas, making sure we know what we're doing, okay, before we talk about vectors and do our acceleration lab next week. Incidentally, reminder, okay, the lab we did yesterday is due on Tuesday, February 12th. Okay, so make sure you're keeping that ready to go. Okay, definition of acceleration. Whenever the velocity of an object is changing, it is accelerating. Okay, that is the definition of acceleration, a change in velocity. All right. Now, if we're talking about not average velocity, I thought I'd fix that. Okay, not average velocity, but uniform acceleration, okay, we mean that the rate at which velocity is changing is constant. All right, so for example, gravity is an example of uniform acceleration. If something falls, it accelerates at 9.81 meters per second squared as long as it's falling, okay, in the perfect physical world. A car accelerating away from a stoplight is not an example of uniform acceleration. Why not? Well, yes, when it reaches the speed limit, yes, it stops accelerating. But I mean, like during the time where it is changing its velocity, why do I not get a graph that's linear? What does a car have that you're changing all the time or changes automatically? Yeah, it's got gears. Okay, each gear accelerates at a different rate. Okay, you probably noticed that if you ever tried to pass somebody on a 2-lane highway. Okay, so you press the accelerator down, your car gears down, looking for a lower gear where the rate of acceleration is greater, giving you the opportunity to get around the car before the oncoming traffic reaches you. Okay, that's the whole idea. How many of you can drive standard? Wow, I think that's the highest number I've had in a class in a long time. Okay, okay, yeah. Driving standard, you get a way better impression of this. Okay, if you just like on the 2-lane highway pull out and leave it in 5th or 6th and try and pass, you'll die. Okay, because the rate of acceleration in 6th gear is very, very low. Okay, you need to gear down to 4th or maybe even 3rd if you really want to get around somebody. Okay, and you don't redline the car and blow the engine. Okay, that's what you're looking for. You're looking for a different gear. Okay, so if I'm looking at uniform acceleration, a velocity versus time graph of that would be linear. Okay, but a velocity versus time graph of a car accelerating away from a stoplight looks like this. It flattens. Okay? If that car was allowed to continue accelerating all the way till its top speed, eventually that line would just be flat because it wouldn't be able to go any faster. Everybody follow me there? But we can see that the rate of acceleration is quite high in 1st gear and maybe even in 2nd gear, but as we get to 3rd and 4th and 5th, and if you've got one of the really new cars that has like a 10-speed transmission, it's like a bike, okay? It just keeps changing gears and giving you different rates of acceleration. All right, that making sense to everybody? Okay, so there's uniform. This is uniform, straight line. This is non-uniform. Okay, the slope is constantly changing, so that's non-uniform. We essentially don't deal with non-uniform acceleration. All of our questions will deal with uniform acceleration because it's simpler. Okay, this is the formula that you learned last year in Science 10. Change in velocity divided by change in time produces acceleration. All right, so that would be final velocity minus initial velocity divided by time gives me acceleration. All right, what were the units for acceleration? Anybody remember? Meters per second squared. Okay. What does that mean? Actually, I don't square the seconds. And that's the danger, is because we see that squared there, that's what we think. Okay, what's really happening here is when I use this formula, I'm dividing meters per second by seconds. Remember, acceleration is the rate at which I change my velocity. That is, how many meters per second do I go faster or slower? Okay, if I'm accelerating due to gravity, every second I fall, I will go 9.81 meters per second faster than the second before, because the rate of acceleration is 9.81 meters per second, or meters per second squared. Okay, the reason we get the squared is because of the division of fractions. If I'm doing this, meters per second divided by seconds, that's the same as saying this. Everyone okay with that? When I divide fractions, I'm supposed to reciprocate and multiply. Okay, so what I end up with is meters per second times 1 over seconds. Meters times 1 is meters. Seconds times seconds is seconds squared. That's where we get those units from. It really just means meters per second, okay? But we always say it as meters per second squared because mathematically that's what it looks like. We don't actually square the time, okay? And that's a common mistake we don't want to make. All right, is that ringing a bell for everybody from last year from Science 10? Okay, so that's a formula you should be fairly familiar with because you would have used it. Now, where did that formula come from? We talked about that yesterday as well. Okay, if this is a velocity versus time graph, okay, this here would be B. Okay, I'm just going to put a point up here. Okay, this will be Y. This will be X. Okay, if I solve for the slope of this line, okay, effectively what I have is VF minus VI over time. Okay, remember that formula is derived as the slope formula from a velocity versus time graph. Okay, so when this is translated out, it is actually this formula, okay, on that graph. Okay, manipulations of this formula. If I want to solve for t, what do I do? Right, basically just kind of cross multiply or swap with a here. Multiply both sides by t, okay? T goes away because t would be on the top, okay? And then divide both sides by a. I'm solving for time. Everybody all right with that? Okay, that's the easy one. I want to solve for VI. What do I move first? Time. Remember the third rule of algebra. Move what's not attached first. T is not attached to VI. Okay, so I want to move T first. So T times A leaves me with this. So effectively, guys, T times A equals the change in velocity. Everyone okay with that? All right, so if I want to find VI, okay, right now I'm subtracting VI. If I move VF, I'll be solving for negative VI. And if that's okay for you, that's fine. I hate solving for negative numbers because I always forget that I'm solving for a negative number and then I get the wrong direction on my answer. Okay, so what I do is I make sure this number becomes positive by adding it to both sides. Now you're probably looking at that and going, Coderre, didn't you, you just made it worse. You were trying to get VI by itself and you just put it over on the other side where there was a bunch of stuff. Yeah, I did. But now it's positive now. Okay, now I don't have to worry about the vector I get for it. Okay, how do I get T times A over there? Nope. Subtract it. Okay, remember that according to order of operations, I would multiply these two numbers before I added it to VI. So I move it as one chunk. Okay, so VI will equal VF minus T times A. Here's why this makes sense. Just a minute ago, we said that T times A equaled the change in velocity. So if I take the final velocity and subtract the change, that should give me my initial velocity. Okay? So if you're like one of those people that likes to talk things through in your head, hopefully that makes sense to you. Okay? If I take the final velocity, subtract how much I changed it by, that will leave me with what I started with. Okay. I want to solve for VF. Should I move T again? Yes, move T first. All right, T is over here. Now I want to solve for VF. What do I do with VI? Add it. Okay, so here's again that talking it through thing. If I take the initial velocity and add the change, that should give me my final velocity. All right, so those are the manipulations of that formula you'd be expected to do. You've probably already done them a bunch of times in Science 10, but just a quick review of how that works. Okay, questions on that formula there? Okay. All right, so this example here, suppose we have this plane and it starts from rest. Now, there's one of those terms you always have to be on the lookout for in a question. Okay, if we say something starts from rest, then VI is 0. If it comes to rest, then, well, yeah, so which thing is 0? If it comes to rest, not VI, but VF would be 0. Okay, but rest always means stopped. Okay, so if you see the word rest, you know that you've got a 0 in there somewhere for a velocity. You just have to be on the lookout for that. Okay, all right, so it starts from rest. Okay, so we know that VI equals 0 meters per second. Okay, the plane accelerates down the runway, and 29 seconds later, so they just gave us the time, okay, attains a velocity of positive 72.2 meters per second. That would be VF. Okay, where the plus sign indicates that the velocity is to the right. Okay, so I'm just going to take that plus out of there and write beside this right so that I have the right vector on there. Determine the average acceleration of the plane. Okay, so right now, can I use the formula I learned last year? Yes, okay, it's the only one you know right now, okay, but VF minus VI over T will give me the acceleration. Now, the importance of writing down your givens is going to become obvious by the end of the day today when you have 5 different acceleration formulas to choose from. By writing down your givens, you should be able to tell automatically which formula to use because it'll be the only one that has the stuff in it you have. Okay, so it's like that whole thing from Sesame Street. Okay, you got to find the things that are like what you have. Okay, one of those things is not like the others, something like that. Anyway, okay, you got to find the formula that has the information you have and the piece of information you're looking for. Okay, so in this case, that's this formula. I don't have to manipulate it because I'm looking for acceleration, so I just have to plug in my numbers. 72.2 minus 0 divided by 29 seconds. All right. All right, so the rate of acceleration of that plane is 2.5 meters per second squared. And that's going to be right because acceleration is a vector quantity and I changed my velocity in a right directed direction. All right, just occurred to me, I forgot to talk to you about significant digits. Okay, how many of you have done significant digits already in chemistry? Okay, good. It isn't any different in physics. Okay, rules are exactly the same. So just, this rule will work 99.9% of the time. Write down your givens. Whatever number has the least number of significant digits, that's the number of significant digits your answer will have. Okay, the 1% of the time that doesn't work is if I'm really mean and I actually give you a number you don't use. Okay, that happens sometimes. You get a number you don't actually use in a calculation, and thus it does not affect your accuracy. Okay, other things to be aware of in terms of significant digits for physics. Counted numbers versus measured numbers. Okay, if I measure something, then there's a degree of accuracy. If I count something, how certain of it am I? 100%. A counted number does not affect significant figures. All right, so if I count the number of people in here, okay, there's like 28 of you, right? I'm certain of that. There's not 28.1 of you, okay? I'm not like, it's not 28 plus or minus one person. I know, I counted every one of you, there's 28, okay? I can be 100% certain of that. If I watch a pendulum swing back and forth and I count that it does that 5 times, I'm 100% certain it was 5 times, okay? I counted it, so it's not a measured value. Only measured values can have significant figures, okay? Everybody all right with that? That's basically all you need to remember, okay? All the other rules are the same as chemistry, same as before, okay? So if you're adding, you go by decimal places. If you're multiplying and dividing, you go by least number, okay? If there's more than one step, it's always the least number of significant figures after that, okay? Pretty straightforward. Can I give you a quick example of a significant figure one? Okay, so in this question right here, I'll use it as the example, okay? 0, I'm 100% certain of. If I have nothing, I can't measure nothing, so that doesn't affect my significant digits. 29 seconds is a measured value. I timed it to plus or minus 1 second, so it only has 2 significant figures, okay? 72.2 has 3 significant figures. There's 3 measured values in that number. My answer cannot be more accurate than my least accurate measured value. So therefore, my answer can only have 2 significant figures, okay? It has to reflect. I can't, by doing math on something, make it more accurate or less accurate. So that's why we have significant figures. It preserves the accuracy of our measured values, okay? All right. So this is what we just did here. Okay, we got 2.5 meters per second squared for our answer. Okay, this would not be considered correct on a quiz or a test though, because I actually indicated in the question that the direction was to the right. Okay, and we need to reflect that. Okay, here are our other acceleration formulas. Okay, so we got the one you learned last year plus these 4. Okay, we're going to go through examples of each one here, okay? But I'm going to talk about where we get these from, okay? We have these 2 first, okay, that kind of look similar, but they're from different points of view, okay? They both solve for displacement, at least in this setup, but one uses initial velocity, the other uses final velocity, and then they've got this 1/2 AT squared thing going on after that, okay? That formula also comes from a velocity versus time graph. Okay, so if I've got meters per second here and seconds here, how do I get displacement off of a velocity versus time graph? Anyone remember? Find the areas of the shapes. Okay, so there's 2 shapes here. This value right here would be VI. This value right here would be our time. So VI times T gets me the area of this box. The 1/2 AT squared calculates average velocity multiplies by time and gives me the area of the triangle. Okay, that's where that one comes from. Everybody with me on that? Okay, this one works the opposite way. So same graph, still meters per second and seconds, but this time it's saying, here's VF. If I take VF and multiply it by T, okay, I will get this entire area here, right? The entire, this whole thing. So what we want to do though is subtract off this triangle, okay? And that's what this is doing, okay? These 2 triangles would have exactly the same area because they're dividing that rectangle in half. So by subtracting 1/2 AT squared, it gets rid of this and leaves me with exactly the same value. Okay. Everybody all right with that? You don't really need to understand that. Sometimes it's just helpful to see it when we're talking about a formula. Where do we get it from? Okay, the issue with these 2 formulas is time is in them, and it's there in 2 places, which can be problematic if you haven't taken Math 20 and you haven't learned factoring yet, okay? Because if you actually have a situation where you have a non-zero value for VI or VF and you're asked to solve for T, you would have to factor the equation in order to find it, to isolate it, okay? Since we can't guarantee that you've taken Math 20 at this point, you are never asked to solve for T using that formula if VI or VF are not 0, okay? If VI or VF are 0, then you will be asked to solve for T, and here's why, okay? I'm just going to delete all my scribbles here. Okay, if VI is 0, what's VI times T? 0. So then the formula is just D equals 1/2 AT squared. And you can solve for T because now T is only in one place. All right with that? Same for this one. If VF is 0, you just have 0 minus that, and you can solve for T because T is only in one place now. Okay? But we won't ask you to solve for T if VI or VF is not 0. Okay, so you just won't run into a situation like that. Okay, another formula, and this one comes up a lot. Okay, we use this one a lot, especially when we get to projectile motion at the end of the unit. Okay, this one is the only acceleration formula that does not require you to have the elapsed time. Okay, it is strictly looking at rate of acceleration, displacement, and the two velocities. Okay, so it's pretty handy if you don't have the time, okay, given to you as a given. Right? It's not very hard to manipulate. It's not very hard to use. You just have to remember that two of your values are squared. If you're solving for either one of them, you'll have to square root your answer. Okay. And then lastly is this one. It looks really complex, okay, and it can only be used, and we only have these kinds of questions, but it can only be used if acceleration is uniform. Because if I take my final velocity, add my initial velocity, and divide by 2, what am I calculating? Average velocity. Okay, that assumes again that the acceleration is uniform. Okay, that's why it can only work for uniform acceleration. Really, all this formula is average velocity times time. It's v equals d over t. Right? We don't use that formula all that much because there aren't a lot of situations where it's particularly useful. Okay, if we have an accelerating object, we like to avoid using v equals d over t. Okay. All right, so those will be the four. They're all on your formula sheet, okay, under the kinematics heading. Is if the acceleration is uniform. Okay, so what I mean by that is if you had a graph like this, you could use it. If your velocity versus time graph looked like this, you couldn't. The acceleration is different in different parts of that. There's this part where it's traveling at a constant velocity. I couldn't use it in that situation. So its applications are, let's say, limited, right? Whereas the other formulas work regardless. Okay. All right. So we're going to go through a few examples here and just get a chance to kind of manipulate these formulas, see how they work, okay, things like that. So we're familiar with using them because these acceleration formulas will be applicable for the rest of this unit and all of the second unit as well. Okay, there's just a lot of stuff that deals with changes in velocity when we're talking about forces, but also when we're talking about projectiles and movement and stuff like that in kinematics. So, okay, they're going to be super important for the next, 3 months or so. Okay, something like that. All right, let's have you write this example down and then we'll walk through it. All right, so you always get a mark in Physics 20 for your givens, okay? And the reason for that is they help you to pick the formula you need to solve the problem, right? So you should always write them down, okay? In this case here, as I'm reading through the question, I have a hybrid car with an initial velocity, so they told me this is VI, of 10 meters per second east, okay? It accelerates at 3.0 meters per second squared east, so that's gonna be A. How long will it take? How long means time. Okay, so I'm looking for that. Okay, for the car to acquire a final velocity, so that's VF, of 25 meters per second, east. All right, everything's east. That's good. I don't have to worry about positives or negatives for this question. Okay, which of my formulas am I going to use? Exactly. This is the one I'm going to start with, okay? The one from Science 10. Change in velocity divided by change in time equals acceleration. I have to manipulate it to solve for time. All right, so all I did was look at what I was given and then look at my formulas to find a formula that had all the stuff in it that I had and the thing I was looking for. All right, so I'm going to manipulate this for time by multiplying both sides by t and then dividing both sides by a. So t will equal 25 minus 10 divided by 3. Okay, so we got 15 over 3. That should take 5.0 seconds. And I have 2 significant figures because the acceleration was only given to 2 significant digits. All right, everybody follow what I did there? All right, so if this was a question on a quiz, you'd get a mark for this. You would have got a mark for selecting the correct formula, a mark for the manipulation of the formula. Sometimes I'm even generous and give you a mark for plugging in the numbers correctly, but not always, okay? And a mark for the final answer, okay? So it could be between 4 and 5 marks for a question like that, as long as you follow all the steps, okay? Is it important to show your work? Yes, we believe it is. Alberta Learning doesn't. That's why the Physics 30 diploma is multiple choice, but well, we're peons. We don't get to make decisions about that. Okay, we believe method is important, so we give you marks for all the steps. Therefore, write all your steps. There's nothing worse than having done an entire question correct, typed in one number wrong, and written down an answer that is wrong, even though you knew full well how to get the answer. Okay, method is important. If you've shown all of your steps, you can still get 4 out of 5 for a question like this, even though you're terrible at entering numbers in your calculator. Okay. That should only cost you 1 mark, not 5. Okay, and I've seen this happen so many times. I had a kid like 6 or 7 years ago. He just refused to show any work. On his final exam, he forgot to put his calculator back in degree mode. Didn't show any work. And as a result, got any question involving trigonometry wrong. He probably did it right, but because his calculator was in radian mode and he didn't notice, which I still don't understand how he didn't notice because his answers didn't make sense, but when you don't show your work, you just miss stuff like that, okay? And you miss out on a hell of a lot of marks. So show your work is the lesson to be learned here, okay? I know it seems tedious sometimes, but it's worth marks. Show it all. No, I mean, he got it right. I either have to give him full marks because he knew how to do it fully, or I have to give him full marks because he's a brilliant guesser, right? Because I mean, the odds of actually, like, if you have a question whose final answer is 2.7 times 10 to the 28th, or something like that, what are the odds you're going to pick that number out of your head, right? Like if you do, you deserve 5 marks for being a brilliant guesser. All right, questions on how that one worked there? Okay, I want you guys to try these 2 right here. Something to keep in mind. Your units have to match in a formula. So if you're given a velocity, for example, in kilometers per hour, but an acceleration in meters per second squared or a time in seconds, you've got to convert things so that their units all match, right? How many people remember how to convert kilometers per hour to meters per second or vice versa? What's the magic number? No, that's just from kilometers to meters. Kilometers per hour to meters per second is what we call a compound conversion. Let's walk through that because that's going to be important. Okay. All right. If I want to convert kilometers per hour into meters per second, I have to convert the time units and the distance units. Okay. As we've already said, if I want to convert kilometers to meters, okay, I'm going to have to multiply by 1,000. Okay. So I'm multiplying by this conversion here. There are 1,000 meters in 1 kilometer. Okay, kilometers cancels. Now I'm left with meters. Everyone okay with what I've done so far? All right. The next thing I have to do is I have to convert hours to seconds. How many seconds in an hour? Everyone wants to say 60, but it's not the right answer. 3,600. Right? Because we all gut reaction, 60 times 60, right? There's 60 seconds, 60 minutes, 60 times 60, 3,600. All right, there are 3,600 seconds in 1 hour. All right, so whatever my number was in kilometers per hour, I've got to multiply it by 1,000 and then divide it by 3,600. Or I could shortcut and I could say 1,000 over 3,600, just multiply by that. Agreed? Or even easier. Is that the same thing? So if I multiply by 1 and then divide by 3.6, can I just divide by 3.6? There you go. There's your magic number. If I want to go from kilometers an hour to meters per second, I divide by 3.6. If I want to go the other way, I multiply by 3.6. Okay, 3.6 is the magic number. Okay. All right. Back to those two questions. You'll need that when you're dealing with at least one of those. Question number 2. Okay, give you a couple minutes to try those, and then we'll walk through them. All right, let's go over this one then. So we have an elk that's moving at a velocity of 20 kilometers per hour, okay? And it's accelerating. So they gave us VI, but they gave it to us in kilometers per hour, and we need it in meters per second. So we're going to go 20 divided by 3.6, and we got 5.5 repeating essentially here, okay? Now, something important here, guys, in terms of significant digits, because we talked about that earlier, okay? Make sure you keep all of your decimal places all the way through all the steps of a question until the very end. Never round off early in a question, okay? You want to keep all those decimal places because if you round off, it could affect your final answer, okay? So keep all your decimal places all the way till the end. All right, so we got, this is north as well. So there's our initial velocity. It accelerates at 1.5 meters per second squared north. Okay, until it reaches its maximum velocity, okay, and that takes 9.3 seconds. Right, calculate its maximum velocity in kilometers per hour. Well, when we first do this, we're going to get it in meters per second because we have to use units that all match. I can't have a velocity in kilometers per hour, an acceleration in meters per second squared, and a time in seconds. They don't speak the same language. Okay, so I will use A equals VF minus VI over T, but I will be manipulating it for VF. So I'm going to multiply both sides by T, and then I'm going to add VI to both sides. All right, so if I go back to my givens now, that's going to mean 5.5 repeating plus 9.3 times 1.5. All right, so I'm getting 19.51 here, but I only have 2 significant figures because the acceleration only had 2. Okay, so I'm going to be looking at 20 meters per second. Okay, which I then have to convert back into kilometers per hour. 20 times 3.6 is 72 kilometers per hour north. Okay, I have to have the north on there because they gave me north in the question. Calvin. I did. I think even if you use the 19.5 is my final answer in meters per second, right? I think it still gives you 72 even if you multiply that by 3.6, doesn't it? Rounds to 7. Gives you 70.22? Okay. Oh, which is why their answer is here and mine's different. Yeah, okay. You're right. I should have left it as 19.5. Whatever, with all those decimals. Yes, you're right. Okay. All right. Any other questions on those? Besides my horrible example of how not to do significant digits just there. I multiplied by 3.6. Okay, so essentially what we're saying here is that you have to multiply or divide meters to kilometers by 1,000, depending on which way you're going. And then there's 3,600 seconds in an hour. So you're multiplying by 1,000 and dividing by 3.6, or the other way around, or 3,600, sorry. So it ends up being multiply or divide by 3.6, depending on which way you're going. All right, I want you to write this one down, and then we're going to walk through it together here. Okay, so don't start it, but just write it down. Okay, so on this one here, we have a cattle train traveling west at 16 meters per second. So that would be where the question starts. So we'll assume that that's VI, 16 meters per second west. And it's brought to rest. What does that tell me? VF is 0, right? Okay, we want to find the displacement, so we're looking for D, okay, of the cattle train while coming to a stop. Okay, that takes 8 seconds. Okay, assume uniform acceleration. Now we said there was only one formula where we had to have uniform acceleration for it to work. Okay, now they also don't give me acceleration in this problem, do they? They give me the two speeds and they give me the time and they want me to find the distance. And they tell me, they go out of their way to tell me it's uniform. So which formula am I looking at here? Okay, if I was looking at a velocity versus time graph of this, it would look like this, right? If I want to find displacement, it's the area of this triangle, right? Would I use then average velocity times time in order to do that? Okay, so does this formula involve using average velocity times time? Yes, it does. Okay, and it's the only acceleration formula we have that doesn't have acceleration in it. And we don't have acceleration for this, so that's the formula we have to use. We have VF, we have VI, we have T, and we're looking for D. All right, you guys seeing the importance of writing down our givens? Okay, we got to match it up with whatever formula we can use here. Okay, so D will equal in this case then 0, that's VF, plus VI, 16, divided by 2, okay, and that takes 8 seconds. So we got 16 over 2, which is 8, times 8 is 64. All right, so the displacement of this cattle train will be 64 meters west. And I think we have just 2 significant figures there, so we're good with 64 meters west. Okay, looking at this formula in terms of manipulation. If I wanted to solve for T, how would I go about doing it? No, I don't want to divide by time because I want time by itself. Leaving it on that side is probably better. If I divide, it'll be on the bottom, right? I can't solve for something if it's on the bottom of an equation. Yeah, I can move this whole thing over here. It's in brackets. Okay, according to order of operations, I have to figure out what this is before I do anything with it anyway. Okay, so I'm really just moving a number over here. I can divide that whole thing over because really what this represents, right? If I wrote it that way, you'd have no problem dividing V over to the other side, right? It's just because it's in brackets and looks more intimidating that we think, oh, I can't move that. I can move it all as one chunk. Okay, this is what it's going to look like. D over VF plus VI over 2. Okay, equals T. T equals D over V, right? Same thing we've done before. All right. What if I want to solve for VF? What's not attached to VF right now? T. All right, so I should move it first. Right? So by dividing both sides by T, I effectively have V equals D over T, right? Average velocity equals D over T. All right, so once I've done that, do I need these brackets anymore? Nope. All right, can I just start picking that apart now? Yeah, multiply both sides by 2 and then subtract VI over to the other side. That'll give me VF. If I wanted to solve for VI, I'd subtract VF over to the other side. Okay, either way will work on that. Okay. These two questions involve using that formula. So give them a try. See how you do with those, and we'll go through them here in a minute. Okay, let's quickly look over at least number 1 here, and we'll see how we do for the second one. So we have a hound running at a velocity of 16 meters per second south. Oh, sorry, not 16.0, 16 meters per second, and that's south. Okay, they slow down uniformly to a velocity of 4 meters per second south. Okay, and they do that in a time of 4 seconds. All right, so for this one here, okay, we're looking for the displacement. So obviously we're using this same formula we just talked about, but we don't even have to manipulate it. Okay, we're just going to plug the numbers in and get our displacement. So we'll have 16 plus 4 divided by 2. Okay, and then we'll multiply that by the 4 seconds. So 16 plus 4 is 20, divided by 2 is 10, times 4, we're going to get a displacement of 40 meters south. Okay, everybody all right with that one? Okay. Now, number 2 illustrates the importance of remembering your vectors. Okay, so we've got a ball that's moving up a hill initially, but afterwards, it's probably going down the hill. Okay, if you roll a ball up a hill, eventually it comes back. Okay, unless you manage to roll it over the top. But okay, it doesn't sound like that's what happened in this question. So we need to keep in mind that direction can change during movement. Okay, so a ball moves up a hill with an initial velocity of 3 meters per second. All right, so I'm going to go VI equals 3.0 meters per second, and I'm going to say that's uphill. Okay, 4 seconds later, okay, and if it's 4 like this, it was counted, not measured. Okay, if it was a measured value, it would have numbers. Okay, because it was written like this, I can just say 4, and that's it. It won't affect my significant figures because obviously somebody went like 1, 1,000, 2, 1,000, and counted it that way. Okay, is moving down the hill at 9 meters per second. Okay, so VF is 9.0 meters per second downhill. All right. We want to find the displacement from the initial point of release. Okay, again, we don't have to manipulate the equation, but we have to keep in mind that my final velocity is down the hill and is thus negative compared to my initial velocity. Okay, so we're going to set up like that. Okay, VF plus VI over 2. So like a -6, okay, divided by 2 is -3, okay, times 4 seconds, and we're going to get that the displacement is 12 meters downhill. Okay, don't like what this one did, leaving that as negative, because negative and positive were not given to you as vectors in the question. Uphill and downhill were given to you, so that's what you should use. It would be wrong, yes. Okay, your vector in the end needs to match the vector you were given. All right, tomorrow we'll be going over the other formulas we didn't get to today, okay, and then we'll see kind of where we're at after that. All right, see you guys later.